I am Anil Kumar. Welcome to my series on calculus. In this video, we will learn about increasing and decreasing functions. We'll talk about increasing and decreasing interval for a function. We'll take examples and practice on these concepts. And then we'll touch upon concavity, relation with its tangent. We'll introduce you to higher derivatives. We'll find the second derivative and then also see how to find the point of inflection. And then we'll have few practice questions from the examination. So let's begin with increasing and decreasing functions. When I say increasing function, it really means what? A function is increasing when it is increasing in its entire domain, right? So that is what is meant by increasing function. Some of the examples are shown in the diagram here. For example, this particular function is increasing, right? You have to see from left to right. So when you watch from left to right, the functions are always increasing. So here, do you see that? So it's increasing all throughout. This is kind of a square root function. It is increasing all throughout. So we can say that function with positive gradient for all values of x are called increasing functions. Now, when I say positive gradient, it really means that if I draw a tangent line, so here, if I draw a tangent line, it's kind of horizontal at this end, and then it is positive and more positive. Do you see that? So in every time, when I'm going from left side to right side, the slope of the line is positive, right? So the slope of tangent is positive. I should say greater than zero. So that is to say that the gradient is positive, right? So the positive gradient. So if on a graph we plot some tangents and find the gradient at any point, it is going to be positive. If it is positive all throughout, in that case, we can say that the function is increasing. Perfect. Now here is an example to understand what is an increasing function and how using calculus we can figure it out. So the question for you is, show that f of x equals to 2x cubed plus 3x minus 10 is an increasing function. You can actually pause the video and answer this particular question. We want to show that this particular function, the cubic function fx cubed plus 3x minus 10, is an increasing function. Now the strategy is we need to find the derivative of this particular function. So if you find the derivative using the power rule, 2x cubed plus 3x minus 10 derivative will be 6x squared plus 3. Now you will notice that 6x squared is always greater than 0. And to this we are adding a value 3. That means that the gradient is greater than equal to 3. Correct? So we can say that the gradient is always positive. It is greater than equal to 3. That means it is always positive. And therefore, it is an increasing function. Is that clear to you, right? So we can say, since the gradient is always positive, the function is increasing. Now here is a graph of this particular function for you to check. So you can see from left side to right side, when I draw a tangent line, let us say I draw a tangent line here, it has a positive gradient. Over here also, it has a positive gradient, and in this position also, it has a positive gradient. So what we see here is that the slope is positive or greater than 0. You can say greater than equal to also, since equal to is considered as non-negative, right? So the slope is non-negative, it is greater than 0. So the function is increasing. You get the idea, right? Now let's take example of a decreasing function also. That will help you to consolidate on our learning. So here the graph which we are showing is a decreasing function. Decreasing function means the value of y decreases, right? As you move from left to right. So it is a very high value here and then it decreases. Perfect. So it is a decreasing function. Now the question for you is here. Example 2. Let's try to focus on this after understanding what a decreasing function is. So, what is the decreasing function? Well, the function with negative gradient means if I draw a tangent line anywhere, in that case, the gradient is going to be negative. It is kind of decreasing. Do you see that? So, if I draw a tangent here or anywhere else, it is going to be sloping downwards. So, it is a negative gradient. Function with negative gradient for all values of x is called a decreasing function. Perfect. So graph shows normally combination of increasing functions, but here we have all decreasing, correct? So all throughout, if it is decreasing, then the gradient will always be less than 0. Now in this example, you need to show that the function f of x equals to 2x plus 1 over x minus 2 is a decreasing function. How will you do it? Well, you have to find the gradient, the derivative, and if that derivative is less than 0 for all values of x in the domain, then the function is decreasing. So let's do it. So here you can see the calculations. We have the function f of x, which is a rational function, 2x plus 1. To find the derivative, we apply the quotient rule, right? So we applied the quotient rule here. Square the denominator and then find the derivative of the numerator times the denominator minus derivative of the denominator times the numerator. Simplify, and when you simplify this result, what do you get? You get negative value, negative 5 over x minus 2 whole square. Since it is negative, denominator is positive, x square, right? Square terms are always positive. The whole thing will be less than 0. Since the gradient or the derivative is less than 0, we can say that the function is decreasing in its domain. Is that clear to you? Perfect. So at this stage, you are very familiar with the power rule, the product rule, the quotient rule. You know how to find the derivatives. Find the derivative of the function and try to simplify it. Once you simplify it, you can always see that if the function is decreasing function, then the derivative is less than 0 for all values of x in the domain. As in this particular case, the derivative is minus 5 over x minus 2 whole square. Denominator being a square will always be positive. Numerator being negative 5 will always be negative. And so negative over positive is going to be a negative number less than 0. Perfect. Now that brings us to another question. Question number 2 for you is find the range of values of x for which the function, let me highlight the function here, x squared plus 6x minus 9 is a decreasing function. So you need to find the values of x for which the given function is a decreasing function. Let me see the question number 1 which we missed in the first page. So the question number 1 is show that the function f of x equals to 2x cubed plus 3x squared is not an increasing function, right? Is not an increasing function. That means the function could be a combination of increasing and decreasing, correct? So I hope you have understood the concept of increasing function where the gradient is always positive. Decreasing function, gradient is always negative. And now let's look into the combination of these. Normally, you will find functions will have increasing and decreasing intervals. In some parts, they will be increasing. In some parts, they will be decreasing. The graph indicates that the function is increasing, right? And then the values start decreasing. So we have a combination of going up and then coming down. So it is combination of increasing and decreasing function, correct? So within intervals, in parts, the function is increasing. In other parts, it is decreasing. Now, there are turning points at which the increasing and decreasing nature changes. So those turning points are very important to consider. So what we have seen here is increasing interval, this interval from minus infinity to this point, which is at minus 4. Let me write down minus infinity to minus 4. We see that the function is increasing. So that will be an interval for increasing. And here we observe that from 0 to infinity, also the function is increasing. Correct? So we have an interval in which the function is increasing. Perfect. From a graph, it is easy to figure it out. Now we will see how to do it when you are given an equation, not just a graph. Okay. Now let's first understand the terms. We'll say increasing interval, the range of the values of x for which the gradient is positive, that is the increasing interval. So in this particular case, the range of the values of x are from minus infinity to minus 4, and that is what we call range of the value of x for which the gradient is positive, right? So it is increasing. Now decreasing will be the range of the values of x for which the gradient is negative. So in our case, the decreasing values are between these two, right? So that is decreasing interval. So from the graph, you could always say from minus 4 to 0, it is decreasing interval. Is that clear? Okay, so from a graph, it is easy. Now the question for you is, which relates to the same graph, that is for you to connect. So question number 3 is, find the increasing and decreasing interval for the function f of x equals to x cubed plus 6x squared minus 20. So I'd like you to pause the video, find the derivative, and then confirm the solution. Is that clear to you? Okay. So we have this particular function which is a cubic function. So derivative of the cubic function is going to be a quadratic in nature. So 3x squared plus 12x is going to be the derivative for the function given to us. We can always factor it. Once you factor, we get 3x plus x plus 4. Now we can analyze this derivative and then figure out parts where it is positive and where it is negative. So let me do that on the side. So what we have here is the derivative of the function, which is 3x times x plus 4. It means there are two zeros. One is at 0 and the other one is at minus 4. So these are the two zeros for the derivative. We're trying to sketch f prime x, right? The first derivative. Since the coefficient, leading coefficient, is positive, the graph of this particular function should be opening upwards. So it will have a graph which is kind of like this. Now from here, it is very clear that the increasing portion is from minus infinity to minus 4 and from 0 to infinity, since we have that portion which is positive. Is that clear to you? And here in between, it is negative. So that is the graph of the derivative as we have marked. Now connect with the definition. Gradient is positive. This is the graph of the gradient, correct? So gradient is positive in the interval from minus 4 to 0. So we say minus 4 to 0, the gradient is positive. So in that case, minus infinity to minus 4, the gradient is positive. And therefore, we can write down that the increasing interval is from when x is less than minus 4 and also when x is greater than 0. We see that the parabola, which represents the gradient, is positive. The in-between portion is the decreasing interval, which is from minus 4 to 0. Is that correct? So this is your decreasing interval. Clear? So that is how you can get increasing and decreasing interval. So what you need to analyze is the gradient, right? So for increasing or decreasing interval, you need to check first derivative or the gradient. Is that clear? So if it is positive, then it is increasing. If it is negative, it is decreasing. Is that clear? So that is how you could frame this in your mind. Okay. So let's move on, and now let's look into a different type of equation. Now this is a very important topic from many examination point of view, especially GCSE. Now here we have a question which is kind of examination style question. Example 3 is function for a given increasing interval. The question is, find a possible value of integer b if the function f of x equals to x squared plus bx plus 1 is increasing in the interval -1 to 1. So at least that means, right? So when you are given such a value, think like it is increasing at least in this interval. Is that clear to you? Right? That means the gradient should be positive in the given interval, which is from -1 to 1. Perfect. So steps involved is write down the function, which we have right here, and then find gradient. So in this case, the gradient is a linear function, 2x plus b. Clear? Now for increasing or positive gradient, which we are interested in, will equate the gradient as greater than 0. That gives you a value of b as greater than -2x. Perfect. Now, we are also given that this gradient should be positive from -1 to 1. So that means if I substitute the value of x as -1, as I did here, I get a condition for b, which is b is greater than 2. Now, I can actually check with plus 1 also. So when I substitute plus 1 here, I get b is greater than -2. Now from these two conditions, which is b is greater than -2 and b is greater than plus 2, what do I conclude? Well, I conclude that b should be greater than 2. So that becomes the solution in my mind. Since we need to find integer value, so integer b, we'll say, well, greater than 2 means b equals to 3. You need to give a possible value. You could give any value, but greater than 2. It could be 3, 4, 5, 6, and so on for the safe side. Is that clear to you? Correct? Now here, I like to add a note. A note is that 0 is considered positive. Clear? So you could give b equals to 2 will also be correct. That will include -1, and so you can try it out. Perfect. So we could have had a condition saying greater than equal to. Is that clear to you? And we could have got this result also. Why am I saying so? In many multiple choice questions, you might be given 2 as the only choice, correct? So it is important to understand this. Now here is your practice question, which is question number 3 for you. I'd like you to pause the video, copy this question, solve it, and then post the solution. It is a very similar question. Find a possible value of positive integer b if f of x equals to 2x squared plus bx plus c is increasing in the interval -4 to 1. Correct? So only change is in the interval, but otherwise same approach. Let's take the next example, which is question number 4 for us. It is based on increasing and decreasing interval. Question is, find the range of value of x for which the gradient of f of x equals to x cubed minus x squared plus 2 is 2x is less than 10. So the function given to you is f of x equals to x cubed minus x squared plus 2x, and the gradient should be less than 10. So in this particular case, we want the derivative of the function to be less than 10. Is that clear to you? So that is what you have to figure out. So it is solving inequalities in a way for the gradient. You can actually pause the video, answer this question, and then check with my solution, right? So simple steps to do this will be write down the function and then its gradient. Once you know what the gradient is, the condition is that it should be less than 10. So equate the gradient to less than 10 and solve the inequality. Bring all the terms to the same side, factor, right? And then write down the solution. Now, couple of ways to do this. I prefer to solve this using the graph itself. So we can have a graph here, let's say a well sketcher of graph. We have two zeros here. One zero is at 2, the other one is at minus 4 over 3. Let's say this point is minus 4 over 3. The other zero is at 2. Since the leading coefficient is positive, the graph should be rising, correct? I mean, opening upwards, kind of like this. And we need the interval, which is positive, right? So it is positive in this part, correct? It is positive in this part, outside, and that becomes part of our solution. So we have the solution right there. Is that okay? So, no, we want less than, sorry. Let me erase this. So we actually looking for less than, not greater than. Okay, the thing is less than, where the gradient is less than. Okay, so since the condition is less than, we're looking for the points which are below the x-axis, which is right there. So that is what the interval. Is that okay? Since we're looking for less than. Perfect. So that is how we are going to answer this particular question. You could also use the interval table to solve the inequality, right? So use the strategies which you learned to solve inequalities for this particular case. Once you get the condition, which is right there, clear. Now here is another test question for you, question number 4, which says graph of y equals to f prime x is given. Means we are giving you graph of the gradient, right? So this is the graph of gradient. You can say derivative or gradient f prime x, right? So graph of derivative f dash x is given. Identify the interval with positive gradient. So in this graph, you need to identify the interval with positive gradient. 4 choices are given to you. You can actually pause the video, answer this particular question, and then look into my suggestions. So let me tell you that these points here are 0, 1, and 2. They're very small to read. So this point is at 1 and this point is at 2. Is that clear to you? Now, the choices are A, minus 1 to 0, B, 0.5 to 1, C, 1 to 1.5, and D is 1.5 to 3. Okay, so post the solutions and I'll check and suggest you. Next, we'll talk about concavity now. So let us consider the graph of a parabola, which is f of x equals to x squared minus 4. So as you know, x squared minus 4 is a parabola which opens upward with vertex at minus 4 as shown. Now let's try to understand this particular graph. It is clear that it opens up and the shape is called concave up, right? So this shape is called concave up, right? Now if I draw tangents at any point on this particular graph, which have been shown here in orange, right? So these are your tangents. You will notice that all these tangents are under the curve. The graph is above the tangents, correct? So what you observe here is that the tangent at any point is below the graph, correct? Now let's look into the gradient. Gradient is the slope of the tangent line. So here the gradient is negative, right? Here the gradient is 0 and now it becomes positive. So that means that the gradient changes from negative value to 0 to a high positive value. Correct? So that really means that the gradient is always increasing. So we can say that the gradient is increasing. Correct? Gradient. And gradient increasing means if we do rate of change of gradient itself, then we can say that the rate of change of gradient is positive. Does make sense? Correct? So we can confirm all this by finding derivative also. So let's find the derivative. So if I write the derivative of this particular function, I get this as 2x. So we know that the gradient is positive since 2 is the coefficient of x, right? So that is what the gradient is, y equals to 2x. Now the gradient y equals to 2x is shown as a line here going through the origin with slope of 2, right? So we see that the gradient is negative in the portion in the quadrant 3 to begin with, then it becomes 0 and then it becomes positive. So we can say that the gradient is increasing. Do you see that? Slope is positive 2, correct? So that shows that the gradient is always increasing. So it goes from high negative value to high positive value. So it is increasing. Secondly, we also see that the tangents on the graph are below the graph. So whenever you have a concave up, right? So this is for concave up. Two things are important to notice. One is the position of tangent. Let me write down tangent below, and derivative increasing. Correct? The gradient increasing. Perfect. Now let's look into the second function, which is with a concave down case. So if I have a function f of x equals to minus x squared plus 4, the graph which we get is concave down. Now in case of concave down, you can see that the tangent at any point is above the graph. So compare the two. Now this is the tangent which is above the graph, another tangent above the graph, third tangent above the graph, as against the previous case where the tangents were below the graph. Correct? Now, look at the gradient. Two things we have to look at. We are looking at gradients and the tangents. Gradients means the rate of change, right? So as you see, the graph is increasing first, then it is 0 and then decreasing. So here, if you draw a tangent, it is positive, high value, right? Then 0. So the tangent changes from, or you can say that the derivative changes from positive value to 0 to negative. So it is decreasing. Correct? And so we can conclude that the gradient is always decreasing for a concave down graph. And the rate of change of gradient, the way it moves, is negative since the line was coming downwards. And this line is for the first derivative, which is what we are calling gradient, right? So the first derivative graph is a straight line coming downwards. Correct? So when it is concave up, we notice that the tangents drawn on the graph are always under the curve. And when it is concave down, the tangents are above the curve. Second, the gradient, I should say, the first derivative is changing from negative to 0 to positive for concave up. Rather, it is increasing all the way. When it is concave down, the first derivative is decreasing. That is what we are trying to do, right? Now, based on this, we have two questions for you. Question number 5. How do you relate concavity, and position of tangent on the curve. So you need to summarize what we have learned in this particular slide. And the sixth question is, what happens at a point where the concavity changes? So it's kind of important to understand what happens at the point where concavity changes. At present, we have taken a case where concavity is not changing. Now the case is, what happens when the concavity changes? And with respect to gradient and with respect to tangent, you should be in a position to explain. Is that clear? Now let me answer this question also for you. Now we'll look into the case. We'll actually review what we just learned. Okay. So we'll again connect the concavity with the gradient and the tangent. So what we learned just now is we could have concave down. This graph is called concave down. In this case, we have a tangent above. Now here we have concave up and we have tangent below, correct? Now here we have concavity changing. So what happened to tangent? You see, it is from concave down to up, right? So this portion here is down and this portion here is up, means concave up. So what happens to a point in between? So if I draw a tangent at this particular point, it crosses the curve. So that is very important to understand. So we have a concave down and a combination with concave up. At a point, the tangent crosses the curve. That is the point which we call point of inflection, correct? And so we are going to define a new point on the curve. So at a point where the concavity changes, the tangent crosses the curve. This point is called point of inflection. Inflection reflecting the change in concavity, correct? So when we have a change in concavity, then at that point the tangent actually crosses the curve and we call this as a point of inflection, correct? So now look into point of inflection in greater details. So in this particular case we have two examples. So let's begin with the very first one, which is graph of the function f of x equals to x to the power of 5. So this is the graph of this particular function. So it is kind of flat at origin. Now at this center portion, what we have is a tangent line as the x-axis. So in this case, x-axis is tangent. Correct? You also observe that the tangent crosses the curve, right? So x-axis crosses the curve. So at this point where it is tangent, it actually goes through the curve. So this point basically by definition becomes point of inflection. Is that clear to you? And you also notice that on either side of this particular point, the concavity changes. This side is concave down and the other side is concave up. Do you see that? So concavity changes. So this is a point of inflection where we have change in concavity. Perfect. So here's the text for you to understand. It does not have any local maximum and minimum point, even though the gradient of the function f dash x, which is equal to 5x to the power of 4, is 0 at x equals to 0, right? So the gradient of this particular function is, the derivative of this particular function is 5x to the power of 4. And so we have a stationary point here, right? So we can write down that the stationary point is at x equals to 0. Since the derivative f dash x is 0 for x equals to 0. right? We have a stationary point. Now, earlier you saw that at stationary point we could have local maximum or local minimum. However, we do not have any maximum or minimum at this particular critical point, right? So at this point, 0, 0, the tangent crosses the curve. The important thing which we have seen at origin, the tangent crosses the curve. Now, such a point where the tangent crosses the curve is called point of inflection. So, in this case, it is a point of inflection, correct? Now, in this part, you might get an idea that if the derivative is 0 and if it is not a maximum or minimum, it should be point of inflection. Well, that would be wrong, okay? It is not an indication. Anyway, there are cases where derivative 0 may lead to point of inflection. Now, here is another example where we have taken a graph. So now we'll consider the graph of the function which is x cubed plus 6x squared, right? So now this is the graph and that is the point where the concavity is changing. Since if I draw a tangent, it crosses the curve, right? However, the tangent slope is not 0, right? So this slope is not 0. So the derivative f dash x is not equal to 0. Do you see that? So, but still we do have a point of inflection. So it is possible to have a point of inflection even when derivative is not equal to 0. So basically, two things are important to understand a point of inflection. One, concavity changes. The other one, the tangent crosses the curve. Perfect. So let's read further. It is important to note that point of inflection may occur when f prime x or the derivative is not equal to 0. Graph of f of x equals to x cubed plus 6x squared has a point of inflection at x equals to minus 2. The gradient of the tangent is negative, not 0, at this particular point as shown in the figure. Perfect. So first derivative does not help in identifying point of inflection. Let me make it very clear. Since with first derivative equal to 0, we have a point of inflection. First derivative not equal to 0, we have a point of inflection. So first derivative is not an indicator for point of inflection. It's kind of important conclusion since in many multiple choice questions you might have a question that the first derivative will help us find what. So four things will be there in which you can always say not point of inflection. Is that clear to you? So what identifies point of inflection? That is what we are going to look into now. So at point of inflection, the concavity changes. That's the key. Since the concavity changes, it is the second derivative which is of prime importance. And we'll look into that part in this video, right? So let's continue with this. So tangent is above the graph. The second thing what we have looking here is if I draw a tangent here, it is above the graph, right? So but on this side, it is below the graph. Do you see that? So here tangent is above. In this case, it is below. So in between, it crosses. So at point of inflection, it crosses. Kind of adjusts from going from above the graph to the below the graph. And that is one of the reasons why the tangent actually crosses the curve at the point of inflection. Is that clear? So that brings us to the next question, which is question number 7 for you. Graph of a cubic function will always have a point of inflection. You need to explain why. Graph of a cubic function will always have a point of inflection. Explain why. Okay, let's move on and understand the concepts of second derivative now before analyzing further on point of inflection. Now we'll take up the same example, which is y equals to x squared minus 4. The derivative of this function is 2x, the gradient, which we say the derivative, right? So many students use the term gradient for derivative. So remember one thing, which is, let me write here, gradient is same as derivative. Let me write first derivative. So in our first lecture on calculus, we described that, right? So we sometimes write gradient also. Dy dx, is the first derivative of this particular function is 2x. Derivative of constant is 0. So gradient is a function which represented by a straight line with a constant slope 2. So on this particular graph, this particular straight line represents the first derivative for the given function which is given in green. So let me write down the function in green. Is it okay? So we have the graph of the function which is right there, and we have a graph of the derivative also on the same coordinate plane. Is that clear to you? Now here you notice two things. One, it is concave up, right? The graph is concave up, and then you see tangent below. And third thing which you notice is gradient rising. Correct? The line. Slope is positive 2. So gradient is rising. So whenever you have a graph which is concave up, the tangent will be below and the gradient will be increasing. Now gradient rising means rate of change of gradient. Do you understand? Will be a constant. So what is this 2? It is rate of change of gradient, right? So that is kind of important to understand. So when you have a function, the gradient is also a function, right? So gradient is also a function. So which is being represented by a line with a constant slope 2. This is the constant slope of 2 for a line, 2x. So gradient is rate of change in position. So as you move along the function, you see that initially up to the vertex, you are coming down. So the slope is negative, which is the portion of the graph shown below the x-axis, negative. And after 0, the slope is positive, which is shown as part of the graph, straight line, after x equals to 0. Clear? Now, when we say that the gradient is increasing, it really means rate of change of the gradient is positive. So what we do is we find derivative of derivative. So that is what it is. So derivative of derivative in this particular case will be derivative of 2x, which is a constant 2. So rate of change of gradient in this case is confirmed to be 2, positive 2. That means the gradient is increasing. Perfect. This rate of change of gradient is called the second derivative and is written as d2y by d2x, right? d2y by d2x. That is how we are going to write it. Now, here's a note here. Let me write down a note, and that is to say not dy by dx whole square, right? Not this. This is different, right? So not this. It is d2y by d2x. That is dy dx whole square is different. Okay. Now since gradient is a function, we can continue to find derivatives of derivative. You could actually have dny over dnx. You can differentiate a function many times. So that basically means that you can differentiate function many times. Is that clear? So we get this term. So that brings us to the next question, which is question number 8. How many times can you differentiate a polynomial of degree n? How many times can you differentiate a polynomial of degree n, right? So is it n? Is it n minus 1? Is it n plus 1? Okay? Or none of them? So one of these is the correct answer. I'd like you to post your solution. Now, let's look into an example relating the second derivative, concavity, tangents, and finding maximum minimum on a given function. So what we have learned so far is we know about the gradient. Let me now take you back to stationary points. So you know what is a stationary point? Stationary point is a point where the first derivative is 0, right? So if f dash x equals to 0, that is called a stationary point. Clear? Okay. So we decide the nature of stationary point by first derivative normally, right? So till now what we have done is we check the first derivative, and if it goes from increasing to decreasing, we know we have a maximum, correct? But if the stationary point we're checking, it goes from decreasing to increasing, we know that is a minimum. Perfect. Now that we did by analyzing the first derivative. Now we'll see how second derivative can help us find out whether the stationary point represents a local minimum or local maximum or neither. That is what we're going to do. Correct? So the nature of stationary point can be confirmed with the second derivative also. If the second derivative is negative, graph of the function will be concave down and the stationary point will be maximum. Correct? So we're saying if the second derivative is negative, then we have a graph which is kind of like this, correct? Concave down, and what we have in this case is a maximum, correct? That is to say, if the second derivative, we could also write like this, is less than 0. Now, the second case is that the second derivative is positive. That is to say that if the second derivative is greater than 0, in that case, the graph will be concave up, right? And that means we have a minimum. Is that clear to you? So simple. So you can find the second derivative at the critical point, and if its value is positive, then we have a minimum. If its value is negative, we have a maximum. So if the second derivative is positive, graph of the function will be concave up and the stationary point will be a minimum, right? So the conditions can be summarized as given here for a stationary point. So stationary point means derivative is equal to 0, well, and the second derivative, if it is less than 0, we know it is a maximum. Now for a stationary point, if the second derivative is greater than 0, then we have a minimum. Perfect. So let's take an example just to verify. So again, I've taken a very simple example with which we had been working. F of x equals to minus x squared plus 4. Now, if I find the first derivative, we get minus 2x. Second derivative will minus 2. Clearly, second derivative is negative. Now that means what? That means negative means that the graph is always concave down, right? Since the second derivative is negative, that is less than 0, the graph of this particular function is concave down. So the graph will be concave down, and therefore we have shown one part, that is, it is always concave down as shown here, and therefore we have a maximum here. Is that clear to you? At any critical point. So the stationary point has been calculated by substituting 0 for the derivative, and therefore x equals to 0, where the function value is 4. So at this particular point, the second derivative is negative, and therefore we have a maximum. Correct? So the stationary point 0, 4 is a maximum since the second derivative is negative at this particular point, as shown here. Perfect. Isn't that simple? So find the second derivative, and if it is negative and the first derivative is 0, then the point will represent a maximum. Question for you here is question number 9. Find stationary points on the curve of the function y equals to x cubed minus 3x squared. So analyze this particular function. Find stationary point really means you have to find the first derivative, right? And equate it to 0. Well, stationary points also include the points where f dash x does not exist. Remember that, okay? Uh, that is for critical numbers. So we actually normally we say critical number. You could have local maximum minimum at critical number. Now, in case of polynomials, we restrict ourselves to stationary points. Polynomials have derivatives at each and every point, right? They're smooth curves. But when we extend it to other functions, we'll change the name to critical numbers. Part B is identify their nature by using two different methods, right? So first find the stationary points, and two different methods you have to use to identify whether they represent a local maximum or a local minimum. So what could be the two methods? You could analyze first derivative and get your result, or you could find the second derivative. Check if it is negative or positive to confirm. Is that clear? Now let's look into example number 6, which is extreme of a second derivative test. So exclusively, we'll see how using second derivative we can confirm that the given function has local maximum or local minimum. So now we will work with another polynomial. It says given the function y equals to x cubed minus 3x squared minus 9x plus 10, find stationary points for the given function. And second part is find the value of second derivative d2y by dx squared at each stationary point and determine its nature. That is to say, if the derivative, second derivative, is positive, then it is a local minimum, concave up. If the second derivative is negative, concave down, the local maximum will be there at that point. Correct? So you can actually pause the video at this stage, solve, and then look into my solution. Clearly, we have the function here, the derivative, factor the derivative to find the stationary point. The two stationary points which we have got are at x equals to 3 and x equals to minus 1. Perfect. Now at each point, you can find the second derivative. So first find the second derivative of the function. The function is 3x squared. The first derivative is, you can also write this as f dash x, correct? And you can write this as f double prime x as the second derivative. So the second derivative is 6x minus x. Now check the value of second derivative for your critical numbers. So two critical numbers, we found that for minus 1 it is minus 12, and for 3 it is plus 12. So this value of negative, which is less than 0, indicates a maximum, correct? So at minus 1, we have a maximum right there. And at 3, we have a minimum right there. Substitute the values of x as minus 1 and 3 to get the y value of your function, and then clearly write down your answer that the maximum is at minus 1, 15, and minimum at 3, minus 17. Correct? So that is how you're going to solve this particular question. So have a good look at the solution. That is how it should be done. And with the second derivative, you can confirm whether your critical numbers are representing local extrema or not. Correct? Another example for you is very similar. So I'd like you to pause the video, copy this particular question. The only thing is I've taken another polynomial. So find stationary points on the curve of the function y equals to x to the power of 4 minus 8x squared. Identify their nature using the second derivative. So the solution has been provided. You can go through this solution. But before that, I would like you to actually solve the question, right? And then check with my solution. Now here you can extend this. Let me write down the extended version of this. So you can extend this to sketch the graph of the function f of x, right? You could do it for the previous function also. You know how to sketch the graph of polynomials. Check their end behavior, zeros, multiplicity of the zeros, and now you know maximum and minimum values. You can also find point of inflection and then sketch. Okay, so as far as the solution is concerned, we basically have the function, find its derivative, and also find its second derivative. Correct? So that is the first step. Find derivative and second derivative. From the derivative, find the stationary points where the derivative is 0. So equating, we got stationary points as -2, +2, and 0, right? So at these stationary points, x values of -2, +2, and 0, we also found the y values, so we know exactly the point. Okay? Now, in the second derivative, substitute the x value for your stationary point, which is -2, 0, and 2. Calculate the values. If it is positive, that means we have a minimum, right? And if it is negative, it is a maximum. So likewise, when you check, you get your solution that there are two minimums in this particular case and one maximum. And there you have your answer that the curve is minimum at 0, 0, and the curve, sorry, maximum at 0, 0, and the curve has a minimum at -2, -16, and +2, -16. Clear? So these additional values will help you to sketch more accurate graph than what you have been doing so far. Perfect. Now let's look into point of inflection. You can add that complexity also and identify the point of inflection and then sketch these graphs, okay? Now coming back to the concept of point of inflection, we learned two things, and that is concavity changes and the tangent crosses the curve. The question here is, we are looking at the point of inflection. We are given the function cube root of x. Confirm that the point of inflection is at the origin, 0, 0. So that's the point. Clearly from the graph, you can see that the concavity is changing, correct? So we have concave up and we have concave down, and therefore this is a point of inflection, clear. But you have to show it and prove it. So the best way to do it is find the second derivative and then check on either side. If the concavity changes, then we have a point of inflection, correct? So what we are going to do is, for the function, we'll find the first derivative. Once we find the first derivative, then you find the second derivative. Is that clear to you? Right? Now we have to look for critical points on the second derivative. Now here, find the critical points. Critical points of the second derivative means that the second derivative is either equal to 0 or does not exist, just as you were doing the analysis of first derivative. Now in this particular case, since the derivative is given to you, f second derivative is given to you right here. So let me rewrite this as -2/9, and that comes in the denominator, right? X to the power of 5/3, correct? So 5/3 cube root, right? 5/3. That is what your second derivative is. Now, clearly, at x equals to 0, we have that it does not exist. So at x equals to 0, it does not exist. So at the point of inflection, we need to now check whether the derivative changes its sign or not. So x equals to 0, it does not exist. We are identifying the second derivative. Second derivative can also be written as f double prime x, correct? take a point. So this is your interval table, right? So we have to use interval table. So we have x equals to 0. On either side, take a point close by. So x equals to -1 and x equals to 1 is a good point. Substitute the value and you get a positive value on the left side. So that means positive value means concave up for positive and concave down for negative. Clearly, the concavity changes from up to down, and therefore we have a point of inflection at x equals to 0. Correct? So I'd like you to go through this solution, understand, and then move on. Now here, there's a very important thing to remember, and that is to say, when the question is point of inflection, then we have to analyze the second derivative. So for a point of inflection may exist at a point where the second derivative does not exist. So in this case, the second derivative does not exist at x equals to 0. It's a critical number and we need to analyze on both the sides. The concavity changes. Therefore, it is a point of inflection. Is that clear to you? Perfect. So that is important to understand, right? Another thing is that we did find the first derivative, but this analysis is not required. So finding critical number, not required. Now I'm mentioning this because the question states only to analyze for point of inflection. So point of inflection means only look for the second derivative and analyze the second derivative. No need to analyze the first derivative. Okay. So that brings us to the end of this particular video where we'll now discuss 4 questions which are based on examination. So I'd like you to pause the video now, copy these questions, solve them. I'll provide you a solution of these questions in my videos. But here are the questions to understand. Question number 1. Find decreasing interval for the function f of x equals to 3 over 10 x to the power of 4 minus 4 over 5 x cubed minus 3x squared plus 36 over 5x plus 11. So when we say decreasing interval, it means what? It means that you have to find the first derivative and that derivative should be less than 0. So interval in which the first derivative is 0 is the decreasing interval. Question number 2. Find the value of b so that the function y equals to square root of x plus 4 plus b over x has a point of inflection at x equals to 3. So when we say point of inflection, that means the second derivative should be either 0 or it does not exist. That is one thing. And second thing is change in concavity. So first, find the critical number for the second derivative and then check with the help of a table of intervals whether the concavity is changing or not, right? So you have to check the change in concavity. Clear? Question number 3. Prove that every cubic function f of x equals to ax cubed plus bx squared plus cx plus d will have exactly one point of inflection and this occurs at x equals to minus b over 3a. Now that is a bonus question for you. Try to do this question and then I'll provide you a solution of this. Question number 4. Sketch the graph of f of x equals to 1 over x squared plus 3. Mark local extrema, means maximum and minimum values, and the point of inflection. So you need to find local maximum and minimum and the point of inflection and sketch the graph of this particular function, right? 1 over x squared plus 3. So I hope that makes sense, right? So what I will do here is I'll provide links for solution videos, right? So you can always check those links and you'll get the complete solution of these questions in those links in the form of videos. So for now, I hope you have understood the concepts of increasing and decreasing, right? So we know what are increasing functions and what are decreasing functions. You have to check the first derivative for this. And also you understand the interval of increasing and decreasing as shown here. The functions could be, decreasing in some places. For example, this function is decreasing in this interval. The other function in red is decreasing in this interval, correct? And in that interval. So the highlighted portions I'm showing here are decreasing. So these decreasing are shown. So these may have some interval, and that is what we talk about increasing and decreasing interval. Then we had few exam practice questions which you need to solve, and then we came to the concept of concavity. In concavity, we learned a couple of things. One, if we have a graph which is concave up, right? So this is the graph which is concave up. So a couple of things here. The tangent will always be below the graph. Is that clear to you? That is the case, right? So, and second thing is the derivative. The second derivative will always be positive. That is what we figured. And if the graph of the function is concave down, in that case, you know that the tangents are above. And the derivative is less than, second derivative is less than 0. Correct? So that is kind of important. And at a point of inflection, the tangent will actually not remain up or down, right? It crosses the curve. It crosses the curve. Right? So in this case, as you can see, the tangent crosses. Here it is up and here it is down, below. I should write above and below, right? So in this case, the tangent is below. In that case, it crosses. Perfect. Now, at point of inflection, the second derivative could be either equal to 0 or it may not exist. So, for point of inflection, it is important to show that the second derivative is either 0 or does not exist, and on either side, the concavity changes. Perfect. So, that is what it is. Now, you also realize that derivative is a function. And so you can have derivative of derivative. And that is what we mean by higher derivative, right? So we are saying derivative of derivative, right? So examples for derivative of derivative are, we can take examples for displacement, velocity, acceleration, right? So we'll take this in another unit where we'll discuss derivative of derivative and take examples based on displacement, velocity, and acceleration. So that is going to be our next unit. Okay. Now we can analyze the second derivative to find or confirm that the stationary points are local maximum or minimum, or critical points are local maximum or minimum. So based on that, we could actually analyze our graph. Now, we'll also see how to find point of inflection on a graph, looking into the strategies learned. And then we had few examination style questions which I like you to try, and then look into my solutions with the links provided. I hope that really helps. Feel free to write a comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.